Alrighty, so today we are going to learn about Avogadro's constant. So, as commonly referred to as this constant is the mole. Now, when you think of mole outside of chemistry, it could be the animal, hyperpigmentation on the skin, mole from Hispanic cuisine, or any other moles. But when it comes to chemistry, a mole refers to a measurement, and the mole is Avogadro's constant. So, what even is his constant? So, his constant is 6.022 times 10 to the power of 23. Now, this is a mole. Now, I understand it's a little hard to wrap your head around the concept of a mole. One of the best explanations that I received is comparing it with something else. So, when you think of the word dozen, you immediately think 12. So, maybe you have a dozen eggs and you think, okay, we have 12 eggs. So, a dozen is 12. But similarly, a mole is 6.022 times 10 to the power of 23. So you can have 1 mole of eggs, which would be a lot of eggs. And this number is extremely large. But the great thing about this number is that we're dealing with chemistry where each atom is so small that such large measurements is extremely necessary. So I'm going to stop drawing eggs, but you get the idea, right? A dozen is only so much, but a mole is that much. So a mole is extremely large. It is a very big number. So now that we kind of know what a mole is, we can go ahead and start doing mole conversions. Now, when it comes to mole conversions, we need to establish some ground rules, which is a sig figs and our constants. So for this video, we will refer to Avogadro's constant as L. So L is Avogadro's constant. Okay, so when we're trying to do mole conversions, we are trying to do something like this. So when we're trying to go from the number of particles to the number of moles, so particles to moles, we're going this way, we divide by L. So once again, we divide by 6.022 times 10 to the power 23. When we're trying to go from the number of moles to the number of particles, so it's this way, we multiply by L. So this chart is extremely helpful towards me, and if you want to write it down, you could, but honestly, it's just common sense. Okay, so we can do an example question, right? So let's say we have 0.020 moles of H atoms. So we're trying to go from moles to particles. Now, if we look back at our chart, when we're trying to go from moles to particles, we go this way. So we multiply by L. So that's simple, right? So you do 0.020 times 6.022 times 10 to the power of 23, and that should give you 1.204 times 10 to the power of 22 H particles. Now, the great thing about a dozen is how it can apply to eggs, or it could apply to stars, or smiley faces, or honestly anything. Similarly, moles can apply to sodium ions, or glucose molecular ideas, or salt. Like, mole can be applied to any of these, or even moles can also be applied to smiley faces and stars. So it's the idea of how this concept of mole, as it's a measurement, it can be applied to a compound or an atom. So that is why when we're going here, we look at particles. We don't say atoms, we don't say ions, we don't say compounds, we say particles. So what am I even trying to say here, right? So we can look at an example. So if I take the same example as above and I say 0.020 moles of C2H5OH. So what are the number of particles in 0.02 moles of C2H5OH? So now I'm trying to go from moles to particles. And when I'm trying to do this, I follow the exact same procedure as I did from the example above. And this is the beauty and the flexibility of the concept of moles. And that is why we refer to the diagram above. We did not write atoms, ions, or compounds. We wrote particles because it is universal. Now here I'm writing molecules because C2H5OH is a molecule. Here, actually, I should have written atoms instead of particles. But you get the idea, right? How the procedure from going from moles to particles was the exact same for if it was an H atom or if it was this scary looking thing. Okay, now we can do it the other way around. So we're trying to go from particles to moles this way. So we need to divide by L. So let's try another example that way, right? So let's say we have 3.01 times 10 to the power of 24. Oops, I meant to write 24 H atoms. How many moles? So when we're trying to do this, once again, looking at our diagram, we divided by Avogadro's constant. So we need to show our work, of course. Times 10 to the power of 23. And when we compute this out, it should be about 5.00 moles of H. Now, we just divided it, but one main things to keep me remember, right? We need to remember our sig figs. These are important. Our final answer needs to have the least amount of sig figs in the question. Secondly, we need to have our units. Moles of what? If I only had so much, moles of what? I cannot just leave it at 5.00 moles. Moles of H. And I could go a step further and write moles of H atoms. And then finally, we need to ensure that we answered the question, which in this last example we did. It asked how many moles and we wrote down the number of moles. So that is the concept of moles and how it is flexible and used from this example and this example, and how it can go from compounds to atoms, but also how we can go from atoms to moles. I hope that you found this helpful.